All right, let's take a look at today. We've got acid-base neutralization. So if we take a look, we can see that the hydrogen ion plus the hydroxide ion makes water. So if we mix, let's say, hydrochloric acid plus sodium hydroxide, we know that these both are things that are aqueous. So if we take a look, we could have, in a sense, H plus aqueous plus Cl minus aqueous, if you recall the net ionic equation from last semester, in A plus OH negative. Both of these being aqueous because they separate out into their ions. That's what they ionize, right? Both of these are strong, so they ionize basically completely in water. So what this is going to form is, it looks like a double displacement reaction, but it's special because you have an acid and a base. We call it a neutralization reaction. The sodium and chlorine and H2O. So the only thing that really is formed new is liquid water. So the hydrogen and the hydroxide formed the liquid water. The sodium and the chlorine are basically spectator ions. We could also write this as NaCl aqueous down here plus H2O, liquid. Good enough. And if we were to cross out our spectator ions up here, we would end up with this neutralization reaction, because that's what's mainly happening there. So as it says, NaCl is salt and H2O is water. And there are many different types of salt. Salt's just a fancy word for talking about ionic compounds. So it says acids mixed with bases make the hydrogen ions react with hydroxide ions to neutralize each other to make water. Scientists use this procedure known as titration to determine the concentration of an unknown acid or base by using the known concentration of the other one to neutralize it. An indicator is used to denote the neutralization through a color change. We use an indicator called phenolphthalein. You guys used indicators using the cabbage juice and stuff like that. Whenever that neutralization occurs, when that color change that you're looking for happens, we call that the endpoint. So, for each of these problems, you should write a balanced equation, and this is some old stoichiometry type of stuff. So this is how many moles of KOH are needed to completely neutralize 1.56 moles of phosphoric acid. So we've got KOH plus H3PO4. That's going to react to form potassium phosphate. We have a +1 charge and a -3 charge. So that's K3PO4 plus HOH, which is H2O. We got 3 potassiums, so we need to put a 3 there. We got 3 hydrogens and 3 hydrogens for a total of 6. So we need to put a 3 there. There's 3 oxygens, there's 3 oxygens. So it's all good. We want to know how many moles of KOH we get. Moles of KOH. And we're going to start with 1.56 moles of H3PO4. Well, every 3 moles of KOH require 1 mole of H3PO4. 1.56 times 3.
It's 4.68.
We get 4.68 moles of KOH. That's pretty easy stuff. Let's drop down to something that might be a little bit more difficult. How many milliliters of 0.45 molar HCl? So we want milliliters of HCl are needed to neutralize 25 milliliters of 1 molar KOH. Well, this has 1 unit, so out of these 3 things that were given, these 3 numbers that were given, the only one that has 1 unit is the 25 milliliters of KOH. So we'll start there. Every 1,000 milliliters of KOH is 1 liter. Every 1 liter of KOH is 1.00 moles. Now I need a balanced equation. So we have HCl plus KOH yields H2O, always going to have water, and the salt here is potassium chloride. Each one with a 1 charge, +1 for potassium, -1 for chloride. So we're good to go. Every 1 mole of potassium hydroxide neutralizes 1 mole of HCl. And every 1 mole of every 0.45 moles of HCl is 1 liter. We want milliliters. Every 1 liter is 1,000 milliliters. 25 divided by 1,000 times 1 divided by 0.45 times 1,000.
That would be about 55.5555.
So 56 milliliters, based off significant digits 0.45 here. 56 milliliters would be required. What if there was a maybe easier way? I don't know if that's the right word. What if there was a different way other than this? Well, there is. There's a formula. If you recall, we have M1V1 equals M2V2. The formula for this is called Ma-Va over Ka, or Ma, molarity of the acid, times the volume of the acid over the coefficient of the acid, equals the molarity of base, volume of base, coefficient of base. To do this correctly, we need a balanced equation. So here we have phosphoric acid. That's where that naming comes in. That's why I taught you how to name. We're going to add that to sodium hydroxide. So again, hydrogen and oxygen hydrogen and hydroxide are going to pair up to form H2O, and sodium is going to go with phosphate. The charge of sodium is 1. The charge of phosphate is 3. So we need 3 NAs there. Since we have 3 NAs there, we're going to need to put a 3 there. 3 H's and 3 H's means we need 6 H's. So that allows us to get the Kub and the Ka. We want the molarity. So we want to solve for Ma. So we're going to divide both sides by Va and multiply both sides by Ca. So the molarity of the base is 0.150 molar. The volume of the base is 38.5. You might be saying, hey, Mr. Jackson, that's in milliliters. That's okay, because watch this. The volume of the acid is 15 milliliters. So milliliters are going to cancel out. The coefficient of the base is 3. The coefficient of the acid is 1. Milliliters cancel out. We're left with molarity, which is what we want. 0.15 times 38.5 divided by 3 divided by 15.
The answer is about 0.1283.
0.128. That's it. You got to balance out the equation, and you can set up either the reaction this way, or you could set up the reaction this way. For Tuesday, I'd like you to do page 11 and page 12. There's the Ma-Va-Va-Ka formula. And there we go. Well, that's it. Have a great day, guys, and I'll see you on Tuesday. Remember, it's important you go through these because we need you to be prepared for the titration laboratory for the rest of the week.